All right, good morning, everyone. Hope you all had a good long weekend. Trying to get caught up on work. That's what I did. Couldn't catch up on my sleep though. All right, so we finished chapters 1, 2, and 3. Um, one more chapter based on inductors and capacitors for DC analysis. That is chapter 4, and then we move on to AC analysis on chapter 5. So my goal is that I would introduce the topic today. We'll go over the theory, the derivations, look at the equations, and then look at the examples on Friday. Okay. The homework for this chapter, I will make due on Sunday night. So again, since we are introducing the topic today, please outside of class, go home and open up the homework and take a look at it. There are some extra credit tutorials. There are some short answer questions and then problems. Okay. All right. So chapter 4, transients. Now, this is an extension of chapter 3. Remember, I said we have inductors and capacitors, which are energy storage devices, right? So we looked at the equations for voltage and current for both inductor as well as capacitor. But the energy cannot be charged or discharged in an instant, right? And so the energy transfer takes a certain amount of time. And in chapter 4, what we're going to look at are equations for the voltage, current, power, and energy during this charging and discharging phase, or the energy transfer phase. Okay, so when energy is being received into and out of the inductor or the capacitor, the voltage and current values keep changing. All right, so we're going to look at that. And I will explain why it's called a transient in just a few slides. Okay, so first thing I want to introduce is the notation. Okay, the circuits, all the circuits will have resistors. You cannot build an electric circuit without a resistor. A resistor allows us to control the current and the amount of energy that is being transmitted in that circuit. Okay, so if you have an inductor along with a resistor, R plus L, it is referred to as an RL circuit. If it is a capacitor, then it's a RC circuit. If you have both, inductor and a capacitor, it is referred to as an RLC circuit. Okay, RLC. So sometimes it gets confusing because RL is used for load resistor, but the L is a subscript. It can also be used for an inductor resistance. Okay, inductor has a resistance. Real life inductors have resistance. So sometimes RL is also used for inductor resistance. It's not that common, and you won't see that in 201. I try to avoid it. And in the lab, you only see it for like one lab. So again, RL can stand for load resistance. RL can also stand for inductor resistance. But in both cases, the L is a subscript. But if you see uppercase RL, then it refers to a resistor inductor circuit. RC is a resistor capacitor circuit. And then RLC, of course, has all three. So you have one energy storage element in a circuit. You have RL or RC. Remember the equations, L di over dt and C dV over dt, right? So when we plug those in to derive our voltage and current, we end up with a first order ordinary differential equations. Okay, it's a first order ordinary differential equation. And so it is known as a first order circuit. Let me change the color. So the solution requires solving a first order differential equation. Hence, the circuit is also known as a first order circuit. So RL and RC are first order circuits. So it's one energy storage component. Now, when we say it's a first, it has one energy storage component, that's not always the case, right? If you have multiple inductors or multiple capacitors in a circuit, and you are able to reduce it down to one single inductor or one single capacitor, that is also considered as a first order circuit, right? We saw in chapters 1 and 2 where you could take a large resistive network and reduce it down to one single resistor. And we saw in chapter 3 at the end where you can take inductors in parallel or capacitors in parallel and a series, and you can reduce it down to one single inductor or one single capacitor. So you could have multiple inductors and multiple capacitors in a circuit, and you could still refer to them as a first order circuit. All right. And then, of course, I talked about how energy is always being transferred into and out of an inductor or a capacitor. So during this energy transfer phase, the charge is being accumulated in a capacitor or an inductor. Hence, when they receive the energy, it is known as a charging phase. And when they give the energy back, we refer to it as being discharge or discharging phase. So when the components are receiving the energy from the source, they are charging. And when they are giving the energy back into the circuit, they are discharging. Okay. So this is receiving, and then this is sending back.
Take it. When you gonna take it?
Please mute whoever's online. And then, as I said, even whether you apply DC or AC for both, the input doesn't matter. But the charging and discharging takes a certain amount of time. And that time, during the time period, the voltage and the current is always has a different value. Okay, always has a different value. But that charging and discharging phase is fleeting. Okay, for instance, we talked about DC, where if you apply a DC voltage to a capacitor, after a certain point of time, the capacitor reaches full charge. Once it reaches full charge, the value of the voltage is steady. The value of the current is also steady. Current, of course, goes to zero. Similarly, for a inductor, if you apply an input current, after a certain point in time, the current reaches a steady state. So the period in time before it reaches a steady state is known as transient, because the values are transient. They are fleeting, they are momentarily available, and hence this is also known as transient analysis. Okay, the values are transient, and so this is also known as transient analysis. Hence, the title of the chapter, transients. Okay, yes. That's a very good point. RLC is a second order circuit. No, it's still an RLC circuit. Not necessarily. For analysis purposes, we sometimes make a lot of assumptions just to keep things simple. And so we reduce it down to like one capacitor, one inductor. Yeah. Okay. So transient analysis. Now, the response of the capacitor and the inductor always follows an exponential form. Okay. So before we get to the equations, I just wanted to show a graph where we're going to identify certain notations. Okay. So on the x-axis, we have time. X-axis will always have time. Before, now this is for charging, right? Both of these are for charging. The charging phases. It doesn't matter whether it's an inductor or a capacitor. The response is always the same, or the form of the response is always the same. So let's say the inductor and the capacitor did not have any stored charge. Okay, so the voltage across the capacitor is 0 volts. The current through an inductor is 0 amps. Right? So at 0 seconds, at 0 seconds, there is no charge, and the value of the voltage, the value of the current is completely 0. And those are your initial conditions. So initial conditions define the setup before you begin your analysis. Now, I'm saying that for this example or this explanation, there is no charge. But as we saw in the previous chapter, if you split up the analysis periods, there could be some initial charge stored in there, right? So we'll take that into account later. But for now, for this explanation, there is no charge. Initial conditions are basically the time at which you begin your analysis. So the conditions right before you begin your analysis are noted by I, initial. Okay. So VI, where I is a subscript, in this case, I does not stand for current. Okay, VI is for initial voltage right before you begin your analysis. II is basically the current before we begin our analysis, the initial current. And again, if the capacitor or inductor is completely discharged, both of these values, VI or II, would be equal to 0 if it is completely discharged or no energy is stored in there. Okay. Now, you begin supplying energy to the capacitor or the inductor, and it begins charging and receiving the energy. At a certain point, it's going to reach, it's going to reach this value. And this value, F, stands for final. So VF or IF is basically the applied input. Applied input. And if you apply 5 volts to a capacitor, you already know that the capacitor should charge up to 5 volts. If you apply 1 amp to an inductor, we already know our final value for the inductor current should be 1 amp. Okay. So that's the final value, and that's the initial value. Sometimes the initial value is also noted as 0. And I don't mean the value, I mean the subscript notation. So, because it refers to the time t equals 0. And again, in this case, the time t equals 0 is the point in time which we begin our analysis. And so sometimes it is noted as V0 or I0. And I will use both in the equation so that students get comfortable with all notations. Okay. So it could be VI or V0. They mean exactly the same. And II and I0 also mean exactly the same. But once it reaches the final value, then this is the steady state region. Okay. This is the steady state region. So after it reaches the final value, the voltage of the current is not going to change. Hence, it is steady state. And the region between the two is the transient region. And the response, basically the voltage and the current in the transient region, is the transient response. All right, let's take a 10-second pause. Let me know if you have any questions. So far, so good. All right. One more thing before we move on. The discharge phase also follows an exponential response. So in charging, we went like this. Discharging, goes like this. The concepts remain exactly the same. You have an initial value, you have a final value. During a discharge, the final value is always 0. Well, unless we interrupt it, of course. When we say a capacitor was applied, had stored energy, and then we let it discharge all the way to 0. So then the initial and final values are flipped. Right? Make sense? All right. Transient response are of two kinds. Again, charging and discharging. So when we have initial stored energy in the capacitor or inductor, and we release it back into the circuit, we call it the natural response. We call it a natural response because that response or the discharging of that energy does not depend on any external source. Okay, it has already received the energy. It is simply discharging that energy back into the circuit. So it is simply discharging the stored energy. So it occurs naturally. Okay, it occurs naturally, hence it is known as natural response. There is no external input. There is no external input to elicit that discharge. And then the other response, and it's not as sinister as the word is being used, it's forced response. Forced is basically an input or external application of the source, which is basically what we have seen so far. You apply a voltage source to a capacitor or a current source to a capacitor or inductor, and then that source will trigger a voltage or current to appear in those components. And they use forced. Okay, it's basically receiving energy from an external input. Basically all sources, which is pretty much what we have done in chapters 1, 2, and 3. We take a voltage source or a current source, connect it to a resistor, and the voltage or current that appears in the resistor would be a forced response, because that response is occurring in that resistor, capacitor, or inductor due to an externally applied input. The source is external to that component. Make sense? So charging is known as forced or step response. The step is because sometimes we deal with these kind of signals where the input signal changes from 0 to some value. So it's either a forced response or a step response, and then discharging is basically a natural response. Natural response. And we look at equations for both. Okay. Natural response circuits is simply a RC circuit where you have a, RC or RL circuit. So this is RL, this is RC, where you have an inductor or a capacitor connected to a resistor, and the stored energy is simply being discharged through that resistor. Okay, so it's simply discharging through the resistor. Now note the subscripts in there. We are using EQ. Okay, so if you have more than one capacitor or more than one inductor in the same circuit, and you are able to reduce it all down to one single capacitor or one single inductor, then it's still, again, it's one component, one energy storage device. And so RC circuit or RL circuits, you're taking the entire circuit into account, meaning all capacitors in there, the total equivalent capacitance, same thing for an inductor, total equivalent inductance, and the same for the resistor. You could have multiple resistors in the circuit. You combine it down to one single resistor and you use REQ. It still remains RL and RC. All right. So it doesn't matter how many components you have. If you're able to reduce it down to one single component, it's still a first order circuit. And if you apply a external source to these circuits, we get the forced response. And applying a source, external source to the circuit. Okay. And this is where the Thevenin and Norton circuits are useful, because you want that source, if it's a large linear network and you have a capacitor somewhere in there, and you wish to determine the response of that capacitor or the inductor for that matter, then you reduce the entire circuit down to its Thevenin equivalent as seen from the perspective of the inductor or the capacitor. And you can take it as one single source and one single resistor. How many of you have taken the lab? And has everyone done lab 5? Lab 5 is the one where you do the RC and RL circuits or RLC circuits, inductor capacitor. Lab 5. The last circuit where you did steady state, you had an inductor and a capacitor in there. Let's say the inductor was not present, but you had one source and then you had multiple resistors in the circuit, and then you had a capacitor at the far end, right? So the circuit was something like this. You had a resistor here, you had a capacitor here, right? Something like this. You had multiple resistors, one source in there. So you could take the capacitor out of the circuit and then describe the rest of the circuit as its Thevenin equivalent. This is very important because the charging and the voltage that is being applied to the capacitor is not the same as your source. If you're applying 10 volts, here, the voltage across that capacitor is not going to be 10 volts. Because the current passes through that resistor, it goes through here, it goes through here. So the actual voltage applied to the capacitor is not 10 volts. Okay, so we need to calculate the Thevenin equivalent voltage that is being applied to that capacitor. That's another application of Thevenin and Norton. Okay, if you have a large circuit and you have an inductor or capacitor in there, your source is not directly being applied to those components. And so you have to calculate the Thevenin voltage and the Norton current for those components. Anyway, so VTH and RTH reduction. And that's why in the examples here, I have VTH and then Norton current. Okay. This diagram shows the shortcut, but this is Norton current IN. Anyway, you connect that source to a capacitor or inductor, and it becomes a forced response circuit. So those are the 4 circuits we're going to look at. A natural response for a capacitor and an inductor, and forced response for a capacitor and an inductor. 4 different circuits, but the equations are all similar. Okay, the equations are all similar, and we should be able to get it done before 10 o'clock, hopefully. All right, so remember switches from chapter 1, right? This is an open switch, and this is a closed switch. So now we use the concept of closing and opening a switch. So it simulates the response, the point in time where you would begin your analysis. Okay, so you'd often see something like this. So what does it mean? The switch is open, arrow is flipped, it's going up. No, arrow is not flipped, sorry. It shows that the arrow is going up and the switch is open, and there is a time value written on there, which is t equals to 0 seconds, or t equals to 0. And what it means is at time t equals 0, the switch is flipped open, meaning prior to time t equal to 0, the switch was closed. Okay? When you see a notation like this, it simply means that t equals 0, the switch is being flipped open. So from that, you should logically understand that prior to 0, the switch was closed. Okay? So for t less than 0, the switch was closed. And that's what it means. That's what you should infer from looking at that illustration. And again, t equals 0 is simply the point in time at which you are beginning your analysis. Okay? T equals 0 is simply the point in time at which you are beginning your analysis. So for t less than 0, if the switch is closed, what do we have? If switch is closed, then excuse me, the current is passing through the inductor, because after it reaches full charge, we don't know how long it has been, but we assume that it has reached full charge. Means sufficient time has already elapsed where the inductor has reached full charge. And when an inductor reaches full charge, it behaves like a short circuit. So it behaves like a short circuit. All of the current IS is flowing through the inductor. Okay, all of the current is flowing to the inductor. All right. The resistor, of course, doesn't have any current. Now, for t is greater than 0, the circuit is flipped open. When you flip open a switch, the circuit changes. And this is very important. Anytime you read in a problem statement that at a certain point in time, the switch was flipped, either open or closed, the circuit changes, you redraw the circuit. That is the absolute first step you do. When you redraw the circuit, it reduces simply to an inductor and a resistor circuit. There is no source anymore. It's simply a RL circuit without any source, right? All of this is cut out. The source and R0 is cut out of the circuit. The only thing left is L and R on the right side. And so now, no source, a fully charged inductor, and a resistor equals a natural response circuit. Meaning the inductor is now discharging through that resistor. Okay? The inductor is now discharging through that resistor. And so the current is going to flow through that resistor until all of the stored energy in the inductor is gone. Does that make sense? Right? Prior to the switch being flipped open, everything was connected. The inductor had full charge. Once the switch is flipped open, you only have a resistor and an inductor. The stored energy in the inductor is now being discharged to that resistor. The initial conditions, IC, notes the initial conditions. Initial conditions, they depend on the initial energy of the inductor. In this case, it is fully charged. Okay, so whatever the source is, that's the value of the inductor current. But here's the notations. We refer to time t equal to 0 at the time at which we begin our analysis, right? This is the point in time where we begin analysis. Now the current through an inductor and the voltage across a capacitor cannot change instantaneously. We already established that, right? So here's another notation that we use for these analysis purposes. 0 plus and 0 minus. Actually, just plus and minus, and then comes the 0. So T plus and T minus, and then because we are referring to time t equal to 0, I would refer to it as 0 plus and 0 minus. The plus and the minus refer to the moment in time that is right after and right before. Okay. So plus is right after or immediately after the specified time, and minus is preceding. So it's right before. And this is very important to note. Okay. T plus and T minus is the time right after and right before. Plus is after, minus is before. So succeeding and preceding moments in time at which you begin your analysis. This is very important to establish the initial stored energy in that inductor or capacitor. We know that the current or the voltage cannot change instantaneously. So for this inductor, if you want to establish the time, the stored energy right after the switch was flipped. Remember, we are beginning our analysis after the switch is flipped. So it's T equals 0 plus, and T equals 0 plus, which is T at 0 plus, would be the same as 0 minus. And again, we do not put a quantitative value on this. We simply say it's right before and right after, but we don't put a value on it. We don't say it's like microseconds or milliseconds or nanoseconds. This is just for the purposes of analysis. So the value of the current or the voltage right before the switch is flipped is the same as the moment it is flipped, and it will remain the same right after it is flipped. And it's important because there's a continuation in all three time moments. And so we say that since the circuit changed after the switch was flipped, the voltage or the current does not change. And the value for this current, I, can be taken before the switch was flipped. And so the current I at 0 plus is the same as the current at I at 0 minus, which we describe as I0, the initial current, which would be equal to a value of that source current. So the important point is when you begin your analysis, especially for a natural response, if sufficient time has elapsed, you can take the maximum charge as equal to the value of the source. Okay, so the initial current through this inductor would be equal to the source current, which is IS. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Nope. All right. Then we apply KVL around the loop. When you apply KVL, we have two voltages. Inductor voltage VL plus VR should be equal to 0. Ignore the signs and everything in there. And again, we're not going to go deep into the explanation or the derivation, sorry. But VL is, of course, L di over dt. VR is simply I times R. And thus, we have a first order ordinary differential equation. Okay. First order ordinary differential equation. Now, this differential equation is not something that we are interested in right now. We are interested in the solution to this equation, right? And thankfully, greater minds have come before us. They've actually done the derivation for us. There is a derivation in the book, and then I have several other books, e-books, where you can actually look it up. So if you're interested, you can let me know, and I will point you in the right direction. But the solution is right here. Remember, for an inductor, we're always talking in terms of the inductor current, right? So we want to find an equation that would describe the value of the current as a function of time, I of t. And so I of t is given by I0 into e, again, exponential form, e raised to minus t over tau. This tau is the Greek letter tau, and it's a constant given by the value of the inductor and the resistor, L over R. It's fixed. It depends on the size of the bucket and the flow of the water, okay? So depending on how large the value of the inductor or the resistor is, the time constant could be small or large, okay? So I of t, the inductor current as a function of time, is given by I0 into e raised to minus t over tau. You could plug in any value of time, t, and you would obtain a value for I, right? T could be anything. T could be 0.1 milliseconds. It could be 100 seconds. And you can obtain a value for the current I. One thing to note is that mathematically, this equation describes the transient response, right? However, you could, as I just stated, you could put any value of time in there. You could put in 1 million seconds, 1 million hours, and you would still obtain a small value for the current I. That is mathematically speaking. That makes sense, right? It'd be 0.000000000, like, I don't know, 20 zeros, 100 zeros, and 1, 2, 3 after that. So mathematically, you would obtain a value, but that's not true in real life. You know, it's eventually at a certain point in time, it's going to get discharged completely. This equation, as beautiful as it is, does not reflect the entirety of the transient response, okay? So when you plug in the values, you will always obtain some value for that current, right? If you plug in tau is equal to 1, you would get e raised to minus 1. You plug in tau is 2, you'd get certain values, 3, 4, 5, 6, and so on and so forth. You'd keep obtaining values. Doesn't matter how far you go for, sorry. T equals 1 tau. T equals 2 tau. Made a hash of it. 2 tau, 3 times tau, and so on and so forth. So it still keep obtaining a values, but by generally established convention, we put a stop to it after 5 time constants. Okay, after 5 time constants or 5 times tau, we say it is fully discharged, because the value remaining would be less than 1% of the original initial starting value. Okay. It would have already lost more than 99.2% of its value, barely left with, 0.7 or 0.8%. And so after 5 times tau, we say that the inductor or the capacitor is either fully charged or fully discharged. In this case, of course, fully discharged. Again, you can have all of these equations on your equation sheet. You don't have to memorize them, but after we go through the entire chapter, the equations will become very familiar. The equations for voltage, power, and energy follow the same form. Voltage V equals I times R. We obtained an equation for the current as a function of time. So then we can write voltage also as a function of time, I of t times R. Okay, I of t times R. Power is the same thing. P equals VI, or in terms of the current and the resistance is I squared times R. So time dependent power P of t also has the same form. The total energy dissipated in the resistor it has to equal, again, we are talking about theoretical, right? It has to equal the total stored energy in that inductor. So we go through the derivation and we come up with the exact same equation, which is half L I square. And the total current that was present in there was the total current present at the beginning of our analysis, which is I0. So half Li0 square. Same equation that we saw in chapter 3. No difference. Right? All of the energy that was stored in the inductor is discharged through that resistor. Make sense? Right? The equations follow the same form. So no difference. So then, oh, writing it down. Any questions? Okay. Then we look at a discharging RC circuit. Again, it follows the same pathway. We have a capacitor. It connected to a source through resistor R1 and resistor R. It charges, and we establish that sufficient time has elapsed. So for t less than 0, capacitor is fully charged. Right? Capacitor is fully charged. And all of the current and everything is flowing through resistor R and R1. Okay. At time t equal to 0, the switch is flipped from the left to the right. And so then after redrawing a circuit, we see that the circuit reduces simply to a charged capacitor and a resistor, and that's it. So it's a natural response of a RC circuit. Okay, natural response for a RC circuit. A fully charged capacitor is now being discharged to this resistor R. And it follows the exact same convention. The voltage across the capacitor right after the switch is flipped, which is V0 plus, would be equal to the voltage right before the switch was flipped, which was V at 0 minus. And we established that as the initial condition, or the voltage V0, and that has a value equal to the source voltage VG. The G in this case simply stands for generator. The subscript does not matter. Basically, it's the source voltage VG. And so once again, we now apply KCL at the top. We can write IC plus IR is equal to 0. IC is C dV over dt plus V over R. We again have a first order ordinary differential equation. When we solve that, we get a very familiar looking equation. V of t voltage across that capacitor as a function of time is given by the expression V0, the total stored voltage times e raised to minus t over tau. Is the exact same expression that we saw for the inductor current. We have the maximum voltage or the maximum current, which is V0 and I0, and then it follows a discharge path of exponential discharge path. So e raised to minus t over tau. And again, we have values for t could be 1 tau, 2 tau, 3 tau, and so on and so forth. When t equals tau, we have e raised to minus 1, e raised to minus 2, e raised to minus 3, e raised to minus 4, and minus 5. And after 5 time constants, we say it is fully discharged. The time constant equation for this is simply the product of the resistor and the current, RC. Okay, RC. So tau for inductor RL circuit is different, and tau for the RC circuit is different. And again, you can have it on your equation sheet. But again, this is the simplest of equations. RC time constant is RC. For an inductor, again, right here. All right, questions? Solutions for the current, power, and energy, again, follow the same function. V equals IR from Ohm's law. And so I is V over R. And so I of t would be V of t over R. The instantaneous power at any given point in time, P is VI, or in terms of the resistor, is V squared over R. And so P of t is V squared t over R. And then energy discharged is half CV square. The voltage is, of course, the total stored voltage in the capacitor, which is V0. So CV0 square over 2, half CV square. The equations are similar. They are exactly the same. They don't change. You can derive it multiple different ways. We still arrive at the exact same equation. Okay. All right, 2 minutes left. We'll do a summary of the natural response. Analysis procedure. The first step is to find the equivalent circuit, meaning you reduce your circuit down to one resistor, one capacitor, or one inductor. Okay. 1 R, 1 C, and 1 L, meaning you find the total equivalent values. And then, of course, you keep an eye on how the circuit changes before and after the switch is flipped. Okay. So you reduce the circuit after the switch is flipped, not before. Then you find the initial conditions. Initial conditions are basically the current for an inductor and the voltage for a capacitor. Okay. Calculate the time constant tau. You have the equations for both, and then you directly write down the solution. That's it, as easy as that. Simply plug in the values in these equations. And then you have your expression for I or V as a function of time for the discharge process. Okay. So first step is redraw the circuit. Second step is to find the time constant, establish the initial conditions, and then simply plug those values into the equations. We only need two values. One is for the time constant tau. The other one is the initial value, which is the stored maximum stored energy in those components. And that's it. Right? And they always follow an exponential form. All right, so we'll end class here today. We'll pick up here on Friday. Crack open the homework. This is sufficient information for you to get started, even without looking at examples. And then again, on Friday, we'll cover the rest of the equations, the other two circuits, and then the examples. And then it's not due until June, but I will make it due on Sunday. Sunday night, most likely. Well, then you'd have an incomplete on your grade. I mean, everyone, not you. And I said all students would have an incomplete, unfortunately. All right, so I'm available for questions if anyone has, and otherwise I'm going to close the meeting.